Okay. Hello guys. This is Nashikant. Actually, today I'm going to just explain about the first task in Spark Foundation, just data analytics and business, data science and business analytics intern. So this task is prediction using supervised ML or supervised machine learning. Okay. So this is a simple linear regression problem. Yeah. So first of all, I'm just introduce what is simple linear regression. Yeah. So in simple linear regression, we have just one dependent variable and one independent variable. So it's very straightforward. We are having one just dependent variable here and one independent variable. So in multiple linear regression, we are having the multiple columns, that is features, and one just dependent variable there, but right now we are just focusing on simple linear regression. And the basic assumptions for the linear regression, that includes the residuals or the error terms, they are normally distributed, right? So we can just analyze this on the data set we are having here. And the residuals are basically, they are the difference between the actual and the predicted value, right? So let's start with that. First of all, we'll start with the step 1, that is reading and understanding the data. So initially we'll just import all the required libraries here, just like NumPy, Pandas, Matplotlib, Seaborn, and these libraries we can import, because initially Pandas is used to just for data manipulation. Just NumPy is for numerical analysis, and Matplotlib and Seaborn, they are used for just visualization. Okay, so here I'm importing warnings also, because I don't want any warning in the when I run the code. Okay, so let's first will just read the URL with the pandas read CSV. Okay, so there are two columns in the data set, hours and the scores. Okay, that means the number of hours studied and what will be the score the student has just got in the on that basis he studied. Okay, so we'll start first of all we'll start with the statistical analysis. So we'll go with the information dev.info, where we are just having 25 entries with the rows, and we're having a 2 columns, right? So we can go with the shape also, 25 and 2, that is 25 rows and 2 columns. And we'll go with the describer. Okay, that will describe the mean, median, mean value is 25%, 50%, 75%, and maximum value, right? So on the basis of that, we are saying there is no just outlier there, because the values are very straightforward. Okay, and on that basis we'll say there is no outlier in the data. Okay, so step 2 is let's visualize the data first. Okay, on that basis we can see what will be the relation between the dependent and the independent variable. Okay, so here I just simply plotted initially just simple linear regression. We having the equation y equal to mx plus c, that m belongs to the just it's a slope and c is the intercept, right? Or in short, we can go with the beta 1 x plus beta 0, right? So let's plot the graph between dependent and independent variable, that is score versus percentage score, hours studied versus percentage score, right? So I will go with the data frames default just plotting, right? Is df.plot, and I'm on x-axis I'm giving hours, and on the y-axis I'm going with the percentage score. Okay, so on after plotting this graph, we are just got this relation straightforward, right? That means we can let's having a straight line here, and on that basis if we plot a straight line through the points, we'll see almost all the points are just having a close to the line, right? So that will say there is a straight relationship between our studied and the percentage score, right? So that will be the one of the just one of the result from the graph, that we'll clearly see from the graph there is a strong relation between two variables, our studied and the score, right? So let's check the C1's inbuilt ridge plot, right? So to show the best fit line, later we will check the plotting manually, right? Okay, Okay, right now we'll go with the step 3, that is performing just simple linear regression. Okay, how to perform the simple linear regression. So initially the equation will state the equation just like equation for multiple. In case of multiple linear regression, we can just say the equation as y equal to c plus m1 x1 plus m2 x2 plus m3 x3 and plus up to mn xn, right? So in this case, y is the response and c is the intercept, and m1 m2 m3 up to mn, they are the coefficients of the features. That is m1 will belongs to a coefficient of feature first feature, and mn belongs to coefficient of nth feature, right? So but in our case, for right now we are not going to focus on multiple linear regression. For our case, we are having simple linear regression. So we'll in case in our case we having equation, the same equation will be converted to y equal to c plus m1 into ours, right? So we have to, and here m1 will be that will be the model coefficient or model parameter, right? So we can go with that, and we'll see what will be the value of m1 here, because will in our case, right? And that definitely will put it out. If we got the value of just m1, then we'll see what will be the effect on y, right? That is our label variable, right? That is dependent variable. Okay, so let's go with the first of all, we'll just build the model using the stats model, right? We'll first build the model using stats model, and afterwards we'll go and build the model with the linear regression, scikit-learn's linear regression just algorithm. Yeah, so we'll just start with the stats model first, and because stat models will give you the features including the p values and all, and on that basis we can do the statistical analysis, right? So okay, so first of all, we first assign the feature variable ours, in this case to variable x, right? And there we will just set the response variable, that is independent, where that is the y response variable will score will just that is the score, right? And we'll just assign it to y, right? So we have initially we have just assigned just ours to x, capital X, and just scores to y, right? Yeah. Right now we'll just go with the splitting the data, right? We'll split it out using the scikit-learn's inbuilt just inbuilt function, that is train test split, right? We'll perform the splitting using the scikit-learn's inbuilt function, that is train test split. So and one more thing, it is very good practice to keep 70% of the data in our train set, and rest 30% will just keep it out as a testing set or validation set, right? So initially we'll go with that, and we'll perform the latter analysis. So initially we'll go with the splitting the data, splitting x and y, right, with the train test split. Here we have just taken x train x test, y train y test, okay, and that is equal to just train test split, and we are going to split x and the y, right? And our training side will be just 70%, that is 0.7, and our testing size will be 30%, that is 0.3, okay? And we'll just keep it out random state as 100, okay? So initially we'll just check it out what will be the x train, okay? We'll go with the dot head, and these are the random values of we are just here we are having index x value, here we having index 12 x value, we having index 4 x value, right? So it will take randomly, right? Because that's why it's called we have taken the random state as 100 definite 100 random splits are there, okay? And we'll get the x train here, okay? Similarly we can go and check the y train also, y train dot head, and these are the corresponding values to the x train, right? That means 9.82, and if x train is 9.82, the corresponding y value will be 88, right? If x is 4.5, the corresponding y value will be 41, right? So these are the corresponding y values, y training values, right? And we have, even though we having a x train and y x test and y test also, but they are we have kept them for the testing analysis, right? Okay, so let's go with the build a linear model, right? We'll build a linear model first. In the first step, we have to import the statsmodels.api library, statsmodels.api, which will perform the linear regression for us, in case of stats model library, right? So we'll import the stats models dot API as SM. Okay, even though one more thing in the stats models, we have to that is one thing which is different from the linear regression is that it will just we have to add the one constant here, right? So by default stats models and stats models just go with the inbuilt function, just inbuilt method, that is ordinary least square, right? It will go with the inbuilt method ordinary least square. Okay, and by default we can add the constant to the training data, right? We have to add constant to the training data. Just once we by default once you have added the constant to the X train data set, you can go ahead and fit a regression line using ordinary least square attribute of the stats model, right? So let's go and add attribute just constant. We can add the constant to the training data and we'll keep it as a X train SM, right? So we'll go with SM dot add constant X train. We are adding constant to the X train, right? Because that with the method add a constant, right? We can add manually. We have to add manually the constant to the X training data, because stats model considered it in stats model we have to add the constant, that is we have to add the intercept, right? C, that is the C value, right? We have that will we have to add manually. Okay, we have to add manually there. So after adding, we can check the extern SM dot head. Right now we have another column, additional column, that is constant, right? Here constant here, and this is the extern column, right? So constant will be one default one, right? Okay, so we'll go with the and here we have just set our regression line here by OLS method, that's ordinary least square. So LR equal to SM dot OLS Y train and X train atom, and we are going with the fitting the line, right, with the dot fit method, right? So after just fitting the line, we can go with the parameters. What are the best parameters, right? Print the parameters, that is intercept and the slope of the regression line. We can print the parameters, that is intercept and the slope of regression line, and we'll go with the LR dot parameters or LR dot param. Okay, and here we are getting this constant value as 1.4951 and ours, or that is X train value, it will be 9.87, right? 9.87. So we are getting the constants here. Sorry, this is the value of M1. Okay, this is the value of M for ours, right? Okay, so default we'll go with summary. We can go with the statistical summary here, LR dot summary. Okay, so here we are getting just R squared, right? R squared value as a 9.957, right? That is 95%, 957, and adjusted R square value as a 0.954, right? That is very good in case of simple linear regression. Okay, and here even though we are checking here p values also, right? For constant p value is 0.64 and for ours p value is 0.0, and that is very good. Okay, in if p value is less than 0.05, right, that is a very good value, right? So here values are concerned with the coefficient and significance, that is p values. Okay, R squared, right, is very, and F statistics and it's significant, right? And all these are everything is included in the summary here. Okay, so we'll go and the coefficient of ours, that is M for ours, is 9.8171 with a very low p value, right? So even though R squared is 0.957, meaning that 95% of the variance is in scores 95%, sorry, 95.7% of variance in scores is explained by us. Okay, so this is a very decent R square value, right? 95% of the variance in the scores is explained by ours, right? Even though F statistic has a very low p value, right, practically low, so meaning that the model fit is statistically significant and explained variance isn't purely by chance, right? Okay, the fit the significant fit, the fit is the significant fit, right? It's let's visualize well model where we can just visualize how well the model fit to the data, right? So how can the model fit to the data, how well it will be fitted. Okay, so let's check it out. From the parameters we got here, we have got this constant parameter as that is the C parameter or intercept value as 4.576, and we got the M value for X train as 9.8717. So we'll get the equation as our initial equation will be y equal to, here we go upper side, we'll go with the initial equation. Our initial equation is y equal to c plus m1 into hours, right? We have got the value of c here and value of m also, so we'll go with that. Okay, and we'll go and check, we having the equation route square is equal to 1.4951 plus 9.87 into hours, right? Okay, so we'll just plot this with the equation. We'll go with the scatter plot x train and y train. Okay, and plt dot plot, we can go with the x train, and y value will be this equation, right? Y value will be this equation 1.4951 plus 9 point into x train, and we'll go with the right color, right? So we are right now we are having the line straight line here, and we see here is a very prominent relation, or very prominent straight line. All the points are very close to the line. Okay, so that is a very good straight line, or very good result for the simple linear regression. Right now we'll go with the residual analysis. What is residual analysis? We have to we have to clear, or we have to just go through the assumptions which are the basic assumptions of simple linear regression. If the assumptions are true, then we are very good to go. Okay, so let's go with the assumptions. The assumptions will one of the assumptions include that error terms are normally distributed, right? What means error term? That is the residuals. Okay, they are normally distributed, right? So we have to prove that, right? So let's go with the we'll just first we'll go and predict the with x10 sm. Okay, well, this training we can go with the training data for predictions. Okay, so we'll go with lr.predict x10 sm, and we can save it in the y train predict. Okay, and round residual will be y train minus y train predict, right? Here we having the residuals here top 5, but okay, right now y train pred, we have to reshape that. Okay, so we go with the dot reshape -1, right? We have reshaped, and right now we having the residuals here, right? And we'll go with the plot the residuals. Okay, so we can go with the distribution plot here, sns dot dis plot residual means equal to 15, and here we are just clearly saying there is a very good prominent it's a very normally distributed here. Okay, so residuals are normally distributed, right? So we just first assumption is very clear here, the residuals are normally distributed, right? So even though we can see here residuals are normally distributed, right? So look, let's go with the pattern. If there is any pattern in the data, we have to check that also. So looking for a pattern in the residual, right? So in the residual, if there is any pattern, so we have to check also that. So we'll go with the plot once again x train and residual. Okay, and we are going to plot just a horizontal line at the 0 at the center, right? And right now we are saying all the there is no just such a pattern, or no such a pattern there in the data, so in the residuals. So no, there is no significant pattern. Okay, as the residuals are scattered around y equal to 0, that means mean of residuals is 0, so the model is good enough, right? Mean of residuals is 0, so the model is good enough. Right now we go with the predictions finally with the test set, right? We can go with the predictions on the test set. Okay, so let's go with the prediction on test set. We can go with the x test sm. Okay, and we have to add constant to testing data also, because we have already added constant to training data, so we have to add to testing data also. So we can add the, here we are adding the constants, and we are giving x10 sm dot head. So we are having x10 sm right now, and we can go with the we can make up just data frame for convenience. Okay, actual and predicted values. So we can go with the PD dot data frame. Actual is y test and predicted is y test pred, right? So y test pred is the predicted value, right? We have here we have predicted that lr dot predict x test sm. So right now this is the actual value and this is the predicted value. So actual is 25, predicted is 28.14. Actual is 35, predicted is 39.00. Actual is 42, predicted is this one, right? So these are the predicted values. So let's go with the, we can use linear regression model also with the, we can use this, you can do the same procedure. Okay, so we can only do with the LR model equal to linear regression, and we can do it LR model dot fit x10 and y10, and finally we can predict with the testing data. Okay, and we having the same actual and predicted, right? So we can get the same values, no difference. Okay, so you can use whatever you want. Okay, and right now what will be the predicted score if the student studies 9.25 hours per day, right? So let me go with hours equal to this one 9.25, and own prediction equal to LR model dot predict this hours and we can print that. Right now we are getting the predicted score as, if the student studies for 9.25 hours per day, then the predicted score will be 92.80. Okay, let's go with the model evaluation. Okay, we can go with the metrics right now: mean absolute error, mean squared error, and R2 score. Right, we can calculate each and everything. So let's go with the R2 score. For training, R2 score will be 9.95%, 0.95, and for testing it's 0.93. Okay, it's very close, right? And for mean absolute error for training is 5.20, and for testing it will be 4.76, right? So mean squared error, definitely for training it will be 30.85, and for testing it will be for 25.67. And right now we go with the last one, that is root mean squared error. Okay, for training it will be 5.5, and for testing it will be 5.0, right? So it's very good results for us. So we can go with this model for, definitely. Thank you.